Good afternoon, class. In today's video, what I'd like to do is to go over the laws of thermodynamics. Now, I do realize that there are 4 of them, and they aren't listed in order of 1, 2, 3, 4. However, this is the historical way of writing it down. The zeroth law was actually the 4th law that was discovered or written down historically. However, they felt that the scientists who wrote it down felt that it was a little bit more fundamental than this first law. So that's why they instead of calling it the 4th law, they called it the zeroth law to put it ahead. So that's why there's that little bit of an odd ordering of the laws of thermodynamics, but that's your little tidbit of history for today. So let us go over each of the laws, and what I will do is I'll do a brief survey of all of the laws, and then as I need to explain more of these laws in depth, I will have more videos in the future to do that. So let's start with the zeroth law. So if you've got 2 objects, and then we'll call them A and B, that are in thermal equilibrium with each other, and object A is in thermal equilibrium with another object, object C, then object B must therefore be in thermal equilibrium with object C as well. Even though you don't have to measure them together, you would know that they are in thermal equilibrium with each other just because object A and object C are in charge. Now, of course, if you're like, Mr. Achiu, that sounds like the transitive property from math, you would be correct. So in that case, basically that's why they felt it was a little bit more fundamental, because it had a math connection. It was just the transitive property, but it dealt with thermal equilibrium. Now, of course, the real question would be, what is thermal equilibrium? So in this case, what we talk about is, and some people might say, oh, thermal equilibrium, that is the temperature of the object. So if the 2 objects are at the same temperature, and the third object will be at the same temperature as either one of them. And that's true, as far as that goes, but it's a little bit more subtle than that, and I thought I'd, let you know what that is. Thermal equilibrium is not really so much a static temperature, like it's just this number, like 55 degrees Celsius or 55 degrees Fahrenheit. It's not like that. Thermal equilibrium means that the exchange of energy between the 2 objects is now even. So whatever is going out of, whatever energy is leaving the object is as the same energy that's coming back in. So there's no new energy being added to a system. For example, in this room there are some ceiling fans, and those ceiling fans are going to, any sweat that would be on my body would get evaporated, and all that energy would be taken away from me, and which is good because that's what helps cool me down when I'm hot. So but if I was in thermal equilibrium, an example of that would be as if I was standing underneath the fans, and but I wasn't getting any cooler. Like I didn't have any sweat left because it was just too dry, or I was already at the body temperature that I wanted to be. So however much heat I'm radiating out is as much heat as is getting pushed into my body from the outside air. So that would be an example of the zeroth law of thermodynamics. Now let's go on to the first law of thermodynamics, which is basically an equation which talks about the change in internal energy of a system is equal to the amount of heat that is put into the system or drawn out minus the work that is done on the system. And of course, this can be positive or negative. Now, remember, either of these numbers could, either heat or work could be positive or negative, and we'll have videos on how to achieve those kinds of things in the future, especially with heat, because right now I'm not defining it, and I'm not gonna even really go into depth on heat, because that is that's worthy of a whole video for itself. Work, on the other hand, I thought would be something to at least try to illustrate with a little example, and that's why I have my little diagram over here. So because the real question is, what is positive work and what is negative work, in fact? So the way that I like to talk about that is, or to illustrate that, is to use my body and when I go swimming. So when I go swimming, if I'm floating on the ocean surface and I take a breath in, I inflate my lungs and my lungs expand. Okay, that means there's now more, so now my volume has increased, and therefore I would float a little bit higher in the water. So, which basically means I'm increasing my buoyant force. This would be called work done by the system, okay? Because I had to put in the energy to increase the volume of my lungs, and I was basically pushing out. You know, I was taking my volume and expanding, so I was pushing against the water, and that's what the system is doing. It's expanding and it's pushing against the environment that the system is in. And notice I'm being very vague and very broad on my terminology, because system, as we defined in a previous video, can be very vague. It could be my whole body. It could be just my lungs. So, you know, keep in mind that knowing what the system is, that actually will determine quite a lot in thermodynamic, you know, when we talk about thermodynamic properties. How to define the system is actually one of the major considerations in order to even start calculating anything about thermodynamics. So now we talk about work done on the system. So this would be when the system is in essence getting crushed, or it's getting something is pressing on the system. So the example would be is if I was a couple miles down in the water, and all of that pressure, all that extra water pressure would not just collapse my lungs and I wouldn't have any breath in me, but it would like crack my bones and basically turn me into a bunch of jelly. So, and needless to say, I would be dead if I was that far down without protection, without a special diving suit that would protect me from that kind of pressure. Yeah, I would be dead. So that would be work done on the system, which would be, so in this case, that would be me in the middle of water with all those tons and tons of extra pressure. It would just compress me. So that's how to think about work done on the system. Okay. Now let's move on to law number 2, which is the law of entropy. So delta S is equal to delta Q over T. So in this case, what we do is we take a constant temperature, and then we find out the change in entropy, which is the change in heat between the system over, you know, divided by that constant temperature. Now, some of you might be wondering, well, what is entropy? And that's a good question, and that will be covered in another video, because this whole second law right here, while I could go over it and tell you all about entropy right here, it's worthy of its own video, so I'm going to save that for another time. So just know that the amount of entropy that is in the system, that has to change, must be proportional to the amount of heat that is exchanged with the system and the environment. One thing that I'll be saying in a little bit as well is to keep in mind that the entropy of a system for every natural process must always go up. So, you know, some people, you might have heard of something called the heat death of the universe, where everything just where entropy just runs rampant and everything just gets completely, you know, disordered because of entropy. And some of you might be thinking, oh, so entropy means disorder. Yes and no. Yes, on a surface level, you can think of entropy as disorder, but it's not really the best way to think about entropy. So and of course, I'll go over that in the next video, or in another video. But the entropy of the universe must always go up with every natural process. So that's one of those things, and I'll explain what that even means in another video as well. So let's go on to the third law of thermodynamics, which is that a system's entropy approaches a constant value as its temperature approaches absolute zero. So what that means is that the system's entropy, you can reduce it, but if you reduce the temperature, you can reduce the entropy. And what that means, and the way you can figure that out, is if you look at it from the second law, if you take that temperature and bring it as close to zero as you can, in order to do that, the amount of heat that has to be in there you must draw heat out of the system. So the entropy, because it's proportional, will go down. However, it cannot get to zero, even if that's why, and so one of the, I guess they would call it the corollary of the third law, is that you cannot get to absolute zero through any number of finite processes. So you could try to pump out all the heat that you can, suck it all out of the system, you will still have a slight temperature no matter how cold you make it. So that concludes that concludes the third law of thermodynamics. And so next time what I'll do is I'll start going over some of these laws in a little bit more detail. So good luck in your studies, and may the force be with you.